Hey, hi again. Um, this is Puya. So I mentioned the half wave inverter and full wave inverter and VD over 2, negative VD over 2. This is positive. Negative VD over 2. We also saw full wave rectifier, which was something like this. And it continues. This was plus VD and negative VD. And I mentioned that, excuse me, full wave inverter has lower harmonics than half wave inverter. So we were just wondering why we create these zero voltages in the full wave inverter. Now I want to show you why this is better than this one. In order for me to show you this, unfortunately for you guys, I have to use Fourier Transform. So I'm gonna give you a very brief review of Fourier Transform first, and then I'm gonna do some analysis on half wave inverter and full wave inverter. So let's see what Fourier Transform tells us. Fourier Transform tells us that if we have any kind of excuse me again, periodic signal, for example, anything like something like this, for example, if we have a periodic signal, let's say this is T, that would repeat itself and it would continue. Any kind of periodic signal, if we have, Fourier Transform tells us that we can write this signal, let's call it f of t, as a combination of bunch of sines and cosines. So Fourier Transform tells us that we can write this signal as a combination, as a summation of the DC value of this signal, whatever it is, plus let's say A1 cosine of 2 pi over t. This is omega f times t plus b1 sine of 2 pi over t times t plus a2 cosine of 2 pi over t times 2 t plus b2 sine of 2 pi over t times 2t. Sorry, I'm running out of space, so I'm going to write it here, plus a3 cosine of 2 pi over t times 3t plus b3 sine of 2 pi over t times 3t plus other multiples of this, what we call fundamental frequency. So it basically tells us that this function that I have, I can write it as a summation of one signal sine and cosine like this, with the period, with the same period. So this is called fundamental frequency. And another signal which has 2 times frequency of the fundamental frequency, the fundamental signal. So it would look like something like this. So this is t over 2, this is t, and the same thing for cosine. And another one, maybe 3 times that this is t. So it would, let me just like do this. So 1 sine here, 1 sine here, 1 sine here. Each of these are 3 over 3, 3 over 3, 3 over 3. The same thing for cosine, 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 and so on. Plus also the DC value, which is the DC offset. So, and these coefficients, so this would be A1, this would be B1, this would be A2, this would be B2, this would be A3, and B3, and so on. It basically tells us that the Fourier series of a function tells us that this function, I can write it as a summation of an infinite numbers of sines and cosines. The first sine and cosine has the same frequency as the original signal, so we call it fundamental components or fundamental frequency components. And the rest of them are basically the harmonics. So they're like signals with multiple frequency of the original signal's frequency. So that's basically the whole point of Fourier transform. The reason we do that is because when we decompose this signal into multiple sines and cosines, we can basically analyze the problem, analyze the circuit, or analyze any problem much easier. Also in electrical engineering or even in mechanical engineering, it gives us the option to design filters, or basically find out like how much of each frequency we have in this signal, right? So for example, in this case, we have this much cosine of this frequency, fundamental frequency, and this much sine of this frequency. So the whole component of the fundamental frequency would be a squared plus b squared, a1 squared plus b1 squared, right? So this is